equilibrium and the state of equilibrium. So what is equilibrium anyway? And it's a process. It's basically the state of reactants and products in concentrations where they're remaining the same or constant in time. And what can be said about the rates in which a system reaches equilibrium? And once the system, the container, the concentration in the container reaches an equilibrium, they basically become the same. The rate at which the reactions occur in the container become the same. They flatline. There's no observable change. And the concentration stays the same over time. When a system reaches equilibrium, are there still changes occurring? Not too much. So let me explain. So here I have my container. And in my container, I have hydrogen and iodine, and they're reacting to form hydroiodic acid. But we're in the same container, so at the same time, hydroiodic acid is decomposing into hydrogen and iodine. And this is happening forward and reverse. And inside the container, it's shifting left, right, left, right. Eventually, the concentrations will remain the same in time, and we will reach equilibrium. And so when we see that on a graph, hydrogen may start up here, okay, and when it starts up here and come down, and its concentration will look like that. Iodine may start here, and over time its concentration will look like that. And hydroiodic acid may not be in the container at all, and then over time its concentration will reach a point of equilibrium. So that's what I mean when I say the system flatlines. Notice how all three of these concentrations right here are not the same. I'm not saying that each molecule inside the container has the exact same concentration. I'm saying the system has reached a point at which everything is equal. It's kind of like holding itself in space and time in a concentration that is the same and equal. It's essentially staying constant. So can changes still occur? I mean, technically yes, because the system is dynamic. If my system right here inside of my container is A plus B, and it reacts to form C plus D, but then C plus D react to form A plus B. The system is dynamic. If I start adding more A and B into the container, then more C and D will be produced. If I add more C and D to the container, I'm going to make more A and B. You know, it's like sitting in a container shifting. So there's three analogies that I like to use in order to describe this. So if you want to try to like visualize it in your head, you know when you're playing a football game and then everyone on the sidelines is kind of like waiting to come in. The team out on the field stays the same, but sometimes someone gets tired. And I'm not going to pretend to know everything about football, but let's just say they get tired. They need a break. So the coach will switch them out. The same number, the same concentration of players is still out on the field. The same concentration of players is still at the bench. But we just start to substitute them out. And we substitute them out equally. And they remain in a constant equilibrium and a constant concentration from the field to the bench. If you can picture two jugglers, like clowns, juggling each other, juggling a ball between each other, one tosses the ball to the other one, simultaneously the one clown tosses it to the first clown, and then they continue to juggle balls. This is kind of the same idea that in a moment in time, someone has the ball, someone doesn't have the ball, the other side has the ball, someone doesn't have the ball. And if you're me, you're a mother, and you go to the mall, and they have these awful things that are called escalators. And your tiny little child right here likes to run up the escalator, at which the escalator is moving down at this point. At the same time, The escalator is going this way, because it's on some sort of loop, and then your little child thinks that it's a party in Macy's, and they're running up the escalator. This child, because they're small and they can't just hop all the way up there, stays at some point on the escalator while the whole system is still technically moving. Okay, that's just Miss Hoskins' example. There's a real example. I like to call the seesaw. So like here's a seesaw, and here's your other. Let me draw that again. All right, a seesaw. They probably don't let these things have been outlawed at the public school system, so you may not have played on one when you were a kid. But if you go to a park that's kind of old school, they still have them. Okay, on the left side we have reactants. On the right side we have products. When the reactants start to outform the products, the seesaw goes this way. And because I'm now starting to make a lot of reactants, I now have room to make more products. And so the product side starts to go this way, and the seesaw comes down, and you have more products versus reactants. And it's just a teeter-totter, back and forth and back and forth, reactants, products. So how do I draw this like on a molecular level? Because I know you all are just thrilled with all of my drawings here. Okay, so here's my molecular level diagram situation. If I have, we'll just say, I'm just going to do a synthesis because it's just easier for me. If I have A2 plus B and I'm going to make AB, then inside of the first one, I have A2 and I add A2 to the container, and then I add B to the container, and some of it reacts, but there's still, if you can't tell, there's still B and there's still A2 in the container, even though there is now AB. Where before there was just B and there was just A2 right there. So it's all mixed in, and this molecular diagram I hope may better illustrate an equilibrium situation where the container looks like this, and then like this, and then like this, and it's just basically sitting there shifting back and forth. All right, that's equilibrium.